Hello, in this video I'd like to try to make sense of regular expressions for tree automata. How can we take our deterministic leaf-to-root tree automata or non-deterministic tree automata and translate them into equivalent, some sort of regular expression? And I find that the best way to get started with regular expressions to motivate them is by looking at the pumping lemma. So suppose that we have some sort of regular language L, and here I'm just talking about ordinary regular languages of words. We're not thinking about trees just yet. And there's some sort of deterministic finite state automaton that recognizes this language that has n states. Then suppose that we have a word that's accepted by the automaton, some sort of word in the language that has more than n characters in it. Then what's going to wind up happening by the pigeonhole principle is the same state is going to show up more than once. We're not sure exactly which state is going to show up more than once or where it's going to show up more than once, but we know that somewhere in our run, in our reading of this word, the same state is going to show up twice. And what this means is that we've found a loop within the transition diagram for this automaton. So we know that reading AB takes us from the start state to state QI, and then reading BA takes us in a loop from QI back to itself, and then reading the character B takes us from state QI to some sort of final state. What we can conclude from this is that the word ABB also has to be accepted by the automaton, because we know that reading the characters AB will take us from state Q0 to QI, and reading the character B will take us from state QI to a final state. We also know that the word AB, BA, BAB will be accepted, because we know that reading AB will take us from the start state to state QI, reading BA will take us from QI to QI, reading BA will just go around the loop again, taking us from state QI to QI, and then reading this last B will take us from state QI to a final state. And in general, the word AB followed by n copies of BA followed by B for any n, for any non-negative integer n, is going to wind up having to be in the language. And the pumping lemma says that anytime we have some sort of word with more characters than the finite automaton has states, we can always break the word up into 3 pieces such that x, y to the nz is in our language for every n. Again, we don't have much control over how this word is going to split up, but we know that there's going to be some way of splitting up the word such that all of these other words also have to be in the language. So this is a good way of starting to motivate the Kleene star, right? We take this particular word here and we're interested in concatenating it with itself some non-negative integer number of times, potentially 0, potentially just 1, potentially quite a lot. And so hopefully it becomes clear that the essence of the Kleene star is finding ways to go from a particular state back to itself. If we have multiple ways of getting from state QI to QI, we'd also like to include those here to talk about taking the concatenation of some number, possibly 0, of words from some collection. This motivates taking the Kleene star of languages. So what does this look like in the tree automaton case? So here I've taken a random tree word and a random deterministic leaf-to-root tree automaton and run the tree word through the automaton. So we get an association of states to each of the nodes. And we're going to want to try to take advantage of the fact that the same state shows up at these 2 nodes here, state 2. we can conclude that this smaller tree here has to have this particular run, and since this was an accept state, has to also be in our regular language of tree words. Right? The operation of our deterministic automaton on this bit here is the same as the operation down here. And then to determine the state of this node here, we look at the fact that its children have states 1 and 2, and it has character A, and that's exactly what's happening here. This node has character A, and these two nodes have states 1 and 2. It has a different character, but that doesn't matter. That doesn't get inputted into our transition function for deterministic leaf-to-root tree automata. So we can remove this intermediate bit of the tree, and we can also duplicate that intermediate bit of the tree. Here I've duplicated this intermediate bit 3 times, and let me actually circle the bits that I've duplicated to make it clear what's going on. So I've taken this bit here that shows up in the original tree between this instance of state 2 and this instance of state 2, and I've just copied it 3 times. And again, you can check that the transitions all work out the same. If this is the run of this automaton and it's accepting, then this has to be the run of the same automaton on this much longer tree word, and it also has to be accepting because it ends in an accept state. So how can we talk about this phenomenon? How can we talk about this piece here? We can describe this piece that's getting duplicated as this tree here, where I've added a special character that's only allowed to appear once in the tree, and is going to be the place where we're going to want to insert either another copy of this tree, if we're making more copies, or a copy of this at the bottom. And I'm going to require that this particular character only appears once within the tree, and it appears at a leaf. And it's natural to be a little bit skeptical of that, particularly the only appearing once condition on this symbol, but I encourage you to try to prove that it's a regular phenomenon. That is, that there's a deterministic leaf-to-root tree automaton that accepts if and only if this particular character appears exactly once at a leaf. And then, in order to make use of this character, I'm going to define the following operation on trees. I'm going to define some sort of concatenation around the character C, or some sort of grafting operation, where we take every leaf that's labeled with a C, with the character C, in one tree, and replace that leaf, replace the node, with the root node of T. So for instance, if we take the box concatenation of this tree here with this tree here, we're just going to take this node here and replace it with these nodes here. I'm going to move this node so that it goes here. And the resulting tree is going to wind up looking like that. We have this bit from this bit up here, and this bit from this bit over here. This is a little bit of a weird operation. If this tree only had one node in it, then the resulting concatenation would just be replacing this node here by this node here. And so we can write this tree here as X concatenated on the symbol box with Y concatenated on the symbol box with Z, where X, Y, and Z are the trees that look like this. And this tree we can write as X box concatenated with Z. We've taken the Y piece and removed it. And this tree we can write as X box concatenated with 3 copies of Y box concatenated with Z. And in particular, we're going to want to say that X box concatenated with Y box concatenated with itself n times box concatenated with Z is in the language for any non-negative integer n. And this is exactly what we were hoping for. Some sort of notion of concatenation and some sort of notion of Kleene star, some sort of notion of taking a tree and concatenating it with itself n times for some n, but we don't know which. And this is going to motivate our notions of concatenation and Kleene star when we start talking about tree regular expressions. Just for completeness though, I would like to state the pumping lemma for tree regular languages. So suppose that we have some sort of tree regular language L, then there's going to be some capital N, specifically enough to ensure that there exists a branch of length more than the number of states of the corresponding deterministic tree automaton. Alternately, you could just directly require that there exists such a branch, such that any tree in the language with at least n nodes can be written as X box concatenated with Y box concatenated with Z. Where Y is non-trivial, you could imagine Y being the tree that's just a single box by itself. It's kind of the equivalent of picking Y to be the empty word in the ordinary pumping lemma. We need to require that Y be non-trivial in order for this to actually tell us anything, such that for any n, X box concatenated with Y box concatenated with itself n times box concatenated with Z is in the language. So we don't get to control how our tree is broken up. If we want to get more insight into how our tree could be broken up in like this in order to get this to happen, we would need to look at the inner workings of the corresponding tree automaton. But we know that there's some way of breaking our tree up like this, such that all of these tree words also have to be in our language. But here's the exciting thing. We can actually do better than just having a linear string of trees of arbitrary length. Suppose that this tree word is in some regular language of trees because when we run the deterministic leaf-to-root tree automaton for that language on this tree, the run that we get, the states that we get, look like this. Here I want to take advantage of the fact that the state 1 appears 3 times within this tree to conclude that this tree, for instance, is in our language because it has an accepting run that looks like this. Again, you can check that all of the transitions that show up in this tree here already show up in this tree here, and because this has to be an accept state, this has to be an accept state, so this tree has to be accepted by the same automaton. And it's easiest to see this if we break this up into its pieces. What I've done is I've taken this tree word here, and everywhere I see a state 1 appearing, I can replace that node with this entire tree because there's a 1 at this node here. And so I've done that replacement a couple of times to produce this tree here. So unlike in the word case where we can only concatenate in one direction, we can actually concatenate in multiple directions. There's a sense in which we want to describe this tree as belonging to this tree concatenated into its boxes some arbitrary number of times, and then with those boxes all replaced by the tree with a single node, and that node is B. We can make formal sense of this as follows. First of all, I'm going to want to extend the concatenation product over a symbol to languages, arbitrary sets of tree words. And if we want to do that concatenation product all we need to do is, this is just like in the case of regular languages of words, we want to take the concatenation of every possible tree word from the first language and every possible tree word from the second language. So for every possible pair, we take the concatenation of those. And again, we can do this over arbitrary symbols, but usually they'll be temporary symbols, such as a box character. And then we're going to want to define recursively the languages of concatenating this tree or an arbitrary language with itself less than or equal to n times, so specifically up to depth n. The base case, if we're concatenating something with itself 0 times over the box character, that's just going to be the box character. This is just to get the recursion to work out nicely. And if we want to concatenate a language with itself less than or equal to n plus 1 times, well, we can either concatenate it with itself less than or equal to n times, or we can concatenate one of these depth n concatenations further with another instance of a member of the language. And just like in the case of regular languages, if we have a single tree word, we're going to treat that as a singleton language. So looking at this example here, I guess there's a bunch of boxes before we do this box concatenation with B to replace the boxes at the end. But looking at this example here, we have a depth 1 concatenation of the tree with itself, a depth 1 concatenation of the tree with itself. Together, this gives us a depth 2 concatenation of the tree with itself. And then we'll concatenate this depth 2 tree and this depth 1 tree onto this tree here to get a depth 3 tree. So it's important to allow less than or equal to n when we do this definition, right, to include this case here, so that we can have trees of different depths merging together. And then to define the Kleene star, we'll take the union over all possible n of this language concatenated into itself less than or equal to n times. This is our Kleene star, and it allows us to define a notion of regular expression for our regular languages of tree words. So first of all, we want the empty language to be a valid regular expression. You can't get this otherwise. And then for every character in our alphabet and possibly some extra dummy characters like a box, we're going to want to include the singleton language that just contains one tree, that just contains one node, which is labeled with that character. Again, exactly the same notational conventions that we had when we were talking about regular expressions of word languages, where we used a single character to represent the language consisting of just one word, that one word being just that one character. We then want to be able to take the concatenation product of two languages over arbitrary characters. As far as I can tell, it's not enough to have just a single dummy character like a box. You need to have multiple dummy characters to be able to concatenate over in order to be able to express all of the regular languages of tree words, I think. We'll also want the Kleene star over arbitrary characters. We'll want, of course, the ability to talk about the union of two regular languages. And then finally, we're going to want some sort of tree construction operation, which I'm going to denote like this. And this represents the set of all trees whose root is an A, and whose left child is some element of L, and whose right child is some element of M. And we're also going to want to make sense of this notation if either L or M is replaced by an octothorpe to denote the root is A and there's just a left child and no right child, and the left child is an element of L, or there's just a right child and the right child is an element of M. Of course, one has to prove that the languages that we can generate in this way are exactly those languages which are accepted by some sort of deterministic leaf-to-root tree automaton or by a non-deterministic tree automaton. The proof is very similar to the regular expressions of words case. We first need to prove that any language that we can generate in this way is recognized by some sort of tree automaton. And then vice versa, we need to have an algorithm for converting tree automata into regular expressions. There are various ways of adapting the algorithms for converting word automata into regular expressions to work for tree automata, and I'll link to some sources down below where you can take a look at the details. Let's go through some examples that cover the key ideas in one of these proofs. We'll start with a really simple example. All of the tree words on just a single character A. There's still quite a lot that we need to specify here. We need to specify 4 entries to our transition function, depending on whether or not there's a left or a right child to a particular node. We'll have one state which is 0, one character which is A, and 0 will be an accept state. If we let L denote this language, then these transitions tell us that the tree words in our language are either just going to be A by itself, right, that comes from this entry here, or it's going to be A as a parent child with just a left child, and that left child is going to be an element of this language. We get that from this transition here, right? The left child has to be something that takes us into state 0, and the elements of our language are all things that take us into state 0 at the root. Or we could have A with no left child and a right child that belongs to the language, or we could have A with 2 children that belong to the language. So this gives us a recursion that defines L, and this is exactly what the Kleene star is designed to do for tree words. We first add in a new dummy character, I'll use X to denote that, and then we take the Kleene star of this over that character, and what that's going to do is it's going to say, okay, start with the character X, and then every time we see a character X, we can replace it by one of these small trees. And then of course we might get some X's as leaves, and then we can keep replacing those with these trees, and we can keep doing that as long as we want. Of course, the trees that we get when we do this process are potentially going to have X's as leaves that didn't get replaced by this X-less tree here. And we want to get rid of those X's, and so we can do so just by taking the concatenation product over X by just the tree A by itself, and that's going to take all of the X's as leaves and replace them by this A. And so this formula here describes the set of all trees with just characters A. Note that we can actually get rid of this A here. If we had a particular X that we were interested in replacing by that A, we could just leave that X alone and then finish up our Kleene star process, and then that X would be left over at the end, and this product here would replace that X by an A. So we don't have to use another recursion of the Kleene star in order to replace that X by the A that was here. We could just replace it by this A here. So what about a more interesting example? Suppose that we have our odd number of A's automaton. This automaton actually describes 2 separate languages. We'll have L0 be the language of tree words that when we run them through this automaton, the root winds up being in state 0, and we'll have L1 be the language of tree words that when we run them through this automaton, the root winds up being in state 1. In other words, L0 is going to be the set of tree words that have an even number of A's, and L1 is going to be the set of tree words that have an odd number of A's. Looking at the table for the transition function gives us the recursive equations L0 equals B, or a tree of the form A with a left child in L0 and a right child in L1. Note that we can write this as A of L0, L1 if you want to write this in line, but I prefer to write it like this when I'm writing on the board because that's what I really mean. or A with a left child in L1, or A with just a right child in L1, or A with a left child in L1 and a right child in L0, or any one of these four possibilities. And we can similarly write a recursive equation for L1 that winds up looking like this. And every one of these terms corresponds to an entry in the transition table. So again, we could think to set up the following situation. The idea is that just like how before we introduced a new variable x, and then we had a bunch of pieces that we could, as much as we wanted to, replace leaves that had an x in them with, we're going to have two different types of pieces. These 9 pieces are of type 0, and these 9 pieces are of type 1. And we're going to start with just an x1 by itself, and every time we see an x1 as a leaf, we can replace it by a piece of type 1, and every time we see an x0 as a leaf, we can replace it by a piece of type 0. The problem is, this isn't what the Kleene star for trees allows us to do. It lets us only pick one character and one set of trees, and arbitrarily replace that character as a leaf with trees in that set. But fortunately, any tree that we can construct by replacing leaves with x0s by pieces of type 0 and leaves of x1s with pieces of type 1 can be constructed by first joining together all of the pieces of type 0 that are next to each other, and then joining the x1s together. Just so that the expression doesn't get too large, I'm going to remove most of these pieces, but you can always put them back and it'll just make the expression that you wind up getting at the end that much larger and more complicated, but in a straightforward way. So again, the first thing that we're going to want to do is join together the pieces of type 0, and the way we can do that is by setting up the equation. So L0 is sort of going to be given by this expression here. And again, we can get rid of this b at the beginning because we always have this b at the end if we want to replace an x0 by it. This isn't going to exactly be L0 because the leaves on many of these trees in this language here are going to have x1s on them. But when we do the replacement of these x1s with pieces of type 1, then we're going to get L0. So this is kind of an expansion of L0. Now that we have this sort of expression for sort of L0, we can replace any instance of x0 by expressions of that form. We can replace all instances of L0 in the recurrence that defines L1 by this formula here. And I've replaced this x1 by L1 to indicate that we're plugging in an element of the language L1 in here. And now we have a straightforward single recurrence like the type that we had in our first example. We replace all instances of L1 with a new symbol, x1, and then we take the Kleene star over x1 to plug all of those together around the symbol x1. And it's this joining together that's what's going to combine our pieces that already got partially combined when we did our joining for L0. And then finally, to get rid of this dummy character on the leaves, we're going to take the concatenation product over the character x1 by the symbol a. And again, just to keep things simple, we can get rid of this a here. We don't need it. So this here gives us a regular expression for the tree words with an odd number of a's in them. And again, I'll point you down below to some sources where you can find the complete proof that we can take any deterministic tree automaton and turn it into a corresponding regular expression. And it might be a useful exercise to try to prove that any tree regular expression can be converted into a corresponding deterministic leaf-to-root tree automaton. So thanks for watching. Please leave any questions or comments that you might have down below, and be kind to each other.